Welcome. In these lessons on AP Computer Science A, Unit 10 Recursion, we'll cover the 6 topics listed here. To jump to a specific lesson, check out the timestamps.
Recursion is a programming technique where an algorithm breaks down the problem into a smaller piece and calls the same method again to solve that smaller piece. Depending on your programming language, you may use the term function or procedure instead of method. For this lesson, I'm going to use the term method. When a recursive method calls itself, it's called a recursive case. When it finishes up without calling itself, it's called a base case. Every recursive method must eventually hit a base case, otherwise it will keep going until it runs out of memory. Before we jump into an example of recursion, let's look at a mathematical algorithm to calculate factorials. If you don't remember factorials, hang in there for 60 seconds and I guarantee you'll be good. So what's a factorial? A factorial is the product of a positive integer multiplied by all positive integers below it. For example, 5 factorial is 5 times 4 times 3 times 2 times 1, which equals 120. Both 0 factorial and 1 factorial are equal to 1. This will be important later. In math class, you learn to calculate factorials iteratively. Let's go back and look at 5 factorial. We start with the 5 and keep multiplying it by n minus 1 until we get to 1. If you stop and think, you could see how you could program this algorithm iteratively using a loop. Now here's where it gets interesting. We're going to use a recursive technique to solve a factorial. We saw that the iterative way to calculate 5 factorial is 5 times 4 times 3 times 2 times 1. But we could also say that 5 factorial is equal to 5 times 4 factorial. After all, 4 factorial is 4 times 3 times 2 times 1. And we can say 4 factorial is equal to 4 times 3 factorial. We can keep this up until we hit 1 factorial, and we know that 1 factorial equals 1. In this algorithm, 1 factorial is our base case because it provides a solution without calling our factorial algorithm again. Let's write this out in pseudocode. I've got the method factalgo that takes in a parameter n. If n is 0 or 1, then we hit the base case and just return 1. If n is greater than 1, we multiply n times the factorial of n minus 1. We calculate the factorial of n minus 1 by calling factalgo again. Now we're going to trace through the pseudocode, and I'm going to play the part of the factalgo method. I'm the first call of factalgo. Let's see what they gave me for n. N is 3, so we're going to solve for 3 factorial. Let's look at the pseudocode. 3 isn't equal to 0, and it isn't equal to 1, so I can move on. However, 3 is greater than 1, so I'll execute the indented line of code. I'm going to multiply 3 times whatever 2 factorial is. To figure out 2 factorial, I'll call factalgo again. Let's see what they gave me for n. N equals 2. Well, 2 isn't equal to 0 and isn't equal to 1, so I can move on. However, 2 is greater than 1, so I'll execute the indented line of code. I'm going to multiply 2 times whatever 1 factorial is. To figure out 1 factorial, I'll call factalgo again. Let's see what they gave me for n. N is 1. Well, 1 isn't equal to 0, but it is equal to 1, so I'm going to execute the indented line of code. I've reached the base case, so I'll just return 1. Now I know that 1 factorial is 1, so I can multiply it by my n, which is 2. 2 times 1 is 2, so I'm going to return 2. Now I know that 2 factorial is 2, so I can multiply it by my n, which is 3. 3 times 2 is 6, so I'll return the final answer of 3 factorial, which is 6. So that's how a computer executes a recursive program. Let's go back and look at the pseudocode again. Notice that each time we make a recursive call, it's getting closer to the base case. It's crucial to write recursive algorithms this way, because otherwise you'll keep making recursive calls until you eventually run out of space in memory and get a stack overflow. Actually, even if you write a recursive algorithm correctly, you can still run out of memory. When we calculated 3 factorial, that resulted in 3 calls to our method factalgo. We were in no danger of running out of memory there. But instead, imagine if you tried 100,000 factorial. You'd need 100,000 calls to factalgo. You'd run out of space on the stack long before you hit the base case. This is one reason that some types of problems aren't well suited to recursion. Now let's look at the program, but instead of pseudocode, it's written in Java. Or JavaScript. Or Python. In the Java, JavaScript, and Python examples, we followed the same recursive algorithm, but with language-specific syntax. Now, you never have to write an algorithm recursively, because any recursive algorithm can also be written iteratively. But sometimes the recursion solution is more elegant. Calculating factorials is a classic example of that. Now, to learn even more about recursion, join me in the next video.
Let's look at this recursive problem. If you want, you can pause the video and solve it. The method enigma has int parameters a and z. If a and z are equal, we hit a base case and return a plus z. If a is greater than z, we get a recursive case and return a plus whatever is returned by a call to enigma that passes a minus 2 and z. Finally, if it makes it down to the last line, it must be that a is less than z. We have an alternate recursive call that returns z plus whatever is returned by a call that passes a and z minus 1. Alternatively, I could have written it this way, and it would behave the same way. I find this second way preferable, but I want you to see the different ways a problem can be written. Let's say a call was made to enigma that passes 8 and 3. 8 gets passed to the parameter a, and 3 gets passed to the parameter z. A frame gets pushed onto the stack. A equals z is false, so we continue on. A greater than z is true, so this frame will return 8 plus whatever is returned by enigma 6, 3. Enigma 6, 3 is pushed onto the stack. A equals z is false, so we continue on. A greater than z is true, so this frame will return 6 plus whatever is returned by enigma 4, 3. Enigma 4, 3 is pushed onto the stack. A equals z is false, so we continue on. A greater than z is true, so this frame will return 4 plus whatever is returned by enigma 2, 3. Enigma 2, 3 is pushed onto the stack. A equals z is false, so we continue on. A greater than z is also false, so we continue on. This frame will return 3 plus whatever is returned by enigma 2, 2. Enigma 2, 2 is pushed onto the stack. A equals z is true. We've reached a base case and return 4. This frame is popped off the stack. Now the next call can add 4 to 3, return 7, and pop the frame off the stack. The next call adds 7 to 4, returns 11, and pops the frame off the stack. The next call adds 11 to 6, returns 17, and pops the frame off the stack. Finally, this call adds 17 to 8 and returns 25. The initial call, enigma 8, 3, has returned 25. In this lesson, you'll learn about tree recursion and binary recursion. The example will be in Java, but you can apply this concept to other programming languages. Some quick facts. Tree recursion is when a recursive method simultaneously calls itself multiple times. There can be 2, 3, 4, or more simultaneous calls. Binary recursion is tree recursion, where it makes 2 calls at once. A well-known binary recursion algorithm that we're going to look at calculates a Fibonacci sequence. The first 2 digits of the Fibonacci sequence are 0 and 1. Later digits are calculated by adding the 2 previous digits. Let's take a look at the Fibonacci sequence. We start out with 0 and 1. Our third digit is the sum of the 2 previous digits, so 0 plus 1 equals 1. Then 1 plus 1 equals 2. 1 plus 2 equals 3. 3 plus 2 equals 5, and so on. This is a problem that's well made for recursion because we calculate our current value by adding the 2 previous values, which can also be calculated by adding their 2 previous values. Let's write some code to calculate the Fibonacci sequence recursively. First, we'll make a method that returns an int and takes in an int parameter called digit. The digit parameter will be what digit in the Fibonacci sequence we're looking for. In the body, we start by writing the base case. If we're looking for digit 1 or digit 2, we're simply going to return digit minus 1. In our recursive case, we're going to add the sum of the 2 digits before the current one. We'll call the same method twice, passing digit minus 1 and digit minus 2 to calculate the 2 previous digits. Here we add a main method that's going to call fib and pass the argument 5, so it'll print out the 5th digit in the Fibonacci sequence. We'll trace it out by drawing a recursion tree. Recursion trees are a useful technique for visualizing and understanding the behavior of tree recursive algorithms, including binary recursion. We start with our first call to fib and pass the value 5. This is not the base case because digits is not equal to 1 or 2. We go to the recursive case and make 2 calls to the same method. We call fib digit minus 1, which is 4, and then digit minus 2, which is 3. You can see how the 2 calls branch off. I usually go down the left tree branch and then go back around and fill out anything I need to. We go to the fib4 node. 4 goes into the digit parameter. We see that it's not 1 or 2, so we're going to make a call to fib3 and then fib2. We go to the fib3 node. 3 is not equal to 1 or 2, so we make a call to fib2 and then fib1. Now we've hit 2 base cases. If we pass fib the value 2, it'll return 1. If we pass fib the value 1, it'll return 0. So now we can add up these 2 values and finish the fib3 node. Fib3 will return 1 plus 0, which is 1. Now we can go back to fib2. We already know what fib2 returns because we can see it from this example. We don't have to look at the code. We can just say that fib2 will return 1. Next, we go back to fib4, which adds 1 plus 1 and returns 2. We also know that fib3 is always going to return 1, so we don't have to create the extra branches on this end of the tree. We just cross out this node and write in 1. And then to calculate fib5, we add 2 plus 1. A call to fib5 will return 3 because 3 is the 5th digit in the Fibonacci sequence. Depending on the problem you are tracing, you may not be able to simply fill in the other parts of the tree. You may have to draw out additional branches, but it's always valuable to see if there's ones that have already been calculated. Another important thing to remember is you're not always going to be adding the 2 calls together. You could be subtracting them, multiplying, dividing, or doing some other operation. Tree and binary recursion have practical applications beyond Fibonacci. For example, merge sort and binary search can use binary recursion. Tree recursion can be used to generate permutations, draw fractals, and solve mazes. By grasping the versatility of these concepts, you can apply them to a variety of programming challenges. Take a look at this binary recursive problem. If you want, you can pause the video and solve it. The method riddle has an int parameter num. It has a recursive case first, where it calls itself and passes num plus 1, then subtracts a second call in which it passes num plus 2. The base case returns the value of num. Let's say we call riddle and pass it the value 2. In this stack frame, num has a value of 2. Num is less than 5, so it makes the calls riddle 3 and riddle 4. In this frame, num is 3, so we make a call to riddle 4 and riddle 5. In this frame, num is 4, So we make a call to riddle 5 and riddle 6. Here, num is 5, so we hit the base case, return 5, and pop this frame off the stack. The riddle 6 call also hits the base case and returns 6. Riddle 4 calculates 5 minus 6 and returns -1. Let's look to see if we can fill anything else out without tracing it. We already know riddle 5 returns 5, so we can just plug that in here. We also know that riddle 4 returns -1, so we can plug that in here. Riddle 3 calculates -1 minus 5 and returns -6. Riddle 2 calculates -6 minus -1, which is -5. So our initial call of riddle 2 returns -5. In this tutorial, we'll explore head and tail recursion. Some important facts to know. Head recursion is when a recursive call happens at the beginning of the method before other processing. Tail recursion is when a recursive call happens at the end of the method after other processing. There are other circumstances where other processing may happen both before and after a recursive call. Our code samples are written in Java, but these concepts can be applied to other programming languages like JavaScript, Python, or C++. Let's start with head recursion. In this snippet, we have a method called mystery that takes an int input and prints the numbers from 0 to the input value in ascending order. Notice that the recursive call happens at the beginning of the method, before other processing. Now let's write a main method and see what happens when we call mystery with the argument 3. A call stack is a LIFO structure, which stands for last in, first out. Pay attention to how new stack frames are pushed onto the top of the stack. The newer frames at the top will be the first to be popped off the stack. We start with a call to the main method and push a frame onto the stack. When main calls mystery 3, another frame is pushed onto the stack with x set to 3. We check if x is greater than 0, 3 is greater than 0, so we make another call to the method. X minus 1 is 2, so we call mystery 2 and push it onto the stack. The system out print line at the end of the method won't be processed until we work our way back down the stack. In this frame, x is 2. We check, is x greater than 0? It is, so we call mystery x minus 1 and push mystery 1 onto the stack. In this frame, x is 1. We check, is x greater than 0? It is, so we call mystery x minus 1 and push mystery 0 onto the stack. In this frame, x is 0. We check, is x greater than 0? It isn't, so we don't make a recursive call. We continue on to the next line and print 0 to the console. Now that we've finished this method, we pop this frame off the top of the stack. We continue down to the next frame and complete the unprocessed portion. Here, x is 1, so we'll output 1. Then we'll pop this frame off the stack. In the next frame, x is 2, so we output 2 and pop it off the top of the stack. We go to the next frame where x is 3, output 3, then pop it off the stack. The call to main completes and its frame is popped off the stack. Now let's look at our second code example, which demonstrates tail recursion. This almost identical method, also called mystery, takes an int input and prints the numbers from the input value down to 0 in descending order using tail recursion. In this case, the recursive call happens at the end of the method after other processing. We start with a call to the main method and push a frame onto the stack. When main calls mystery 3, another frame is pushed onto the stack with x set to 3. We print x and output 3 to the console. We check, is x greater than 3? It is, so we make another call to mystery x minus 1. We call mystery 2 and another frame is pushed onto the stack with x set to 2. We print out the x value, which outputs 2 to the console. We check, is x greater than 0? It is, so we make another call to mystery x minus 1. We call mystery 1 and another frame is pushed onto the stack with x set to 1. We print out the x value, which outputs 1 to the console. We check, is x greater than 0? It is, so we make another call to mystery x minus 1. We call mystery 0 and another frame is pushed onto the stack with x set to 0. We print out the x value, which outputs 0 to the console. We check, is x greater than 0? It is not, so we don't make the recursive call and finish up this run of the method. We pop the frame off the top of the stack. Next, we finish up mystery 1 and pop the frame off the stack. We finish up mystery 2 and pop the frame off the stack.
We finish up mystery 3 and pop the frame off the stack. The call to main completes and its frame is popped off the stack. You can see the ordering of the outputs is opposite to our head recursion example. Let's take a look at the full Java code for both the head recursion and tail recursion mystery methods side by side. As you can see, the primary difference between the two methods is the placement of the recursive call. In head recursion, the call occurs before the other processing, while in tail recursion, the call occurs after the other processing. Now let's examine a third code example, which demonstrates a method that combines both head and tail recursion techniques to showcase their effects within a single code snippet. In this mystery method, we'll first increment the input value by 1 and print it. Second, we make the recursive call. Finally, we decrement the input value by 1 and print it again. This allows us to see the effects of both head and tail recursion in a single code snippet. For practice, try it on your own. I'll leave the solution in the video description. At first look, this problem can seem overwhelming, but we're going to go through it, make some notes, and then it will be much more manageable. I encourage you to consider this approach when looking at a difficult problem. If you want, you can pause the video here and solve it. Also, if you want to learn more about how recursion works, check out the link to the playlist. The puzzle method has one string parameter called word. The return type is void, so it won't return anything, and an explicit return statement is optional. The recursive case is in the middle of the method. The base case is implicit. With a void method, you don't have to have an explicit return statement. The method will automatically return nothing when it reaches the end. This piece of code will execute as soon as the method is called. It will run as we are going up the stack. This piece of code will execute after the recursive call above has finished. It will run as we are coming back down the stack. Now let's look at what each piece of code does. Having a Java reference sheet handy can make this easier. This line will print out the value of the word parameter, except for its last character. If word has more than 3 characters, puzzle will be called again and will be passed the value of word without the first character. Remember, word will have different values in different stack frames. This piece of code prints 1 star for each character in the word. It uses print instead of print line, so all the stars will be on the same line. After the for loop is done, a print line will go to the next line. Suppose a call was made to puzzle and the string drosty was passed. A frame is placed on the stack, and for this frame, word is set to DROSTE. DROST is output to the console. Don't confuse what is output to the console to the value of the word variable. Word has a length of 6, which is greater than 3, so puzzle is called and passed ROSTE. A frame is placed on the stack, and for this frame, word is set to ROSTE. ROST is outputted to the console. Word length is greater than 3, so puzzle is called and passed OSTE. A frame is placed on the stack, and for this frame, word is set to OSTE. OST is output to the console. Word length is greater than 3, so puzzle is called and passed STE. A frame is placed on the stack, and for this frame, word is set to STE. ST is output to the console. Word length is not greater than 3, so a recursive call is not made. We continue on and print off 3 stars, then a new line. We reach the implicit return at the end of the method and pop the frame off the stack. Back to this frame, we pick up where we left off. It prints 4 stars and pops the frame off the stack. On this frame, we pick up where we left off. It prints 5 stars and pops the frame off the stack. On this frame, we pick up where we left off. It prints 6 stars and pops the frame off the stack. This is what we got when we passed the string drosty. As an extra challenge, figure out one of the following and tell me in the comments. First, what could be a value we could pass when we called puzzle that would cause a compile time error where the program wouldn't even start to run? Second, what value could cause a runtime error index out of bounds exception? Third,
what value could cause a runtime error, null pointer exception. If you have any questions or want to share your experience with Recursion, feel free to leave a comment below. To keep learning, click on the next video. Otherwise, check out the full playlist. See you soon.